Thomas Jefferson National Accelerator Facility is a laboratory for basic nuclear physics research operated by the U.S. Department of Energy. At Jefferson Lab, scientists can advance our understanding of matter itself by probing quarks and gluons in the atom's nucleus with beams of electrons from the superconducting accelerator. Jefferson Lab has an educational mission as well. The Jefferson Lab Science Series features scientists and engineers who are gifted in making their work not only informative but fun. The Science Series is held once a month in the Jefferson Lab Auditorium. The presentation is live, spontaneous, and unrehearsed.
Hello. I'd like to welcome you also. My name is Fred Dilla. I'm one of the physicists here at Jefferson Lab, occasional lecturer at this series. It's good to see such a nice crowd here tonight. We have a very special lecturer for a very special year. Come back to that in a minute. Our lecturer is Dr. Lawrence Krauss. He is chairman of the Physics and Astronomy Department at Case Western Reserve. And I could read 2 pages of his credits. He is a very well-known, internationally recognized physicist that has more than 200 publications in a variety of fields that stretch from the very little, the essence of particle physics, the kinds of physics that we study here at Jefferson Lab, to the nature of the universe. How old is it? How big is it? Where did it come from? Where is it going? But I won't tell you about those things. I want to spend a minute about Dr. Krauss's other career. He has devoted much of his last decade or so in trying to take very esoteric physics and explain it to people like myself who don't study astrophysics or particle physics, and to people like you who are not physicists. He has published a number of very interesting, well-read books on explaining physics to the lay audience. Some of you may have even read them. If you haven't, I encourage you to go get his books and read them. His first book was, now I have to put on my glasses so I don't mess up the title. His first book was called The Fifth Essence. That sounds esoteric. The Search for Dark Matter in the Universe. He's going to come back to that in today's lecture. The next book you may have heard of, Fear of Physics, or you may have suffered from it. The next one we used in our advertisement for this lecture, The Physics of Star Trek. And he followed that up with another book, Beyond Star Trek. And he's multi-talented. That has gone on to liner notes he has written for a CD on music from Star Trek, where he got to meet William Shatner. I'm very jealous. His most recent book is entitled Atom, An Odyssey from the Big Bang to Life on Earth and Beyond. And when you write a book, if we write a book, we're scientists here, we're lucky if 400 or 500 people buy it. If you write a book for the lay scientific audience, it's doing really well if 100,000 copies are sold. And for some of Lawrence's book, 250,000 have been sold. Now, if you can talk PBS into picking up the video rights for that book, then you're looking at an audience of about 15 million. And I'm happy to say Dr. Krauss is in the middle of a project with PBS on his book, The Odyssey from the Big Bang to Life on Earth and Beyond. And we're looking forward to seeing that come out in PBS in the next year or so. Now, why were we anxious to get Professor Krauss back here? He's spoken to this audience before. This is a special year. This is the 100th anniversary of Einstein's miracle year. Tomorrow, March 17th, 1905, Albert Einstein published the first of 3 papers. These 3 papers were published in a period of about 6 weeks, and they revolutionized all of physics. You may have heard of only one of them, called the Special Theory of Relativity. That was one of these papers published in 2005. But he also published a paper on Brownian motion, which was one of the first direct evidence that atoms exist. Believe it or not, there were still people 100 years ago who didn't believe in atoms. And the second paper was on the photoelectric effect, which had a lot to do with proving that something called quantum theory existed. So this one man revolutionized all we knew about the world, and it's gone on with these three papers to be the basis of modern electronics, lasers, and our understanding of the universe. So it's a very special man, a very special year. We have invited a very special lecturer to tell you about what is commonly termed in the physics literature Einstein's greatest blunder. Professor Krauss.
Thank you. Thanks for coming here tonight on this beautiful evening. I came here, I thought it'd be warm coming down from Cleveland, but I guess it wasn't. I'm going to talk about Einstein's biggest blunder, but it was just his birthday yesterday, in fact, or 2 days ago, I guess, and I was in New York City celebrating his birthday. And so on his birthday, you shouldn't talk about blunders. So I'm going to talk about it, but I'm not going to emphasize the blunder part necessarily. What I want to emphasize is the second part of the title, which is a cosmic mystery story. Because what I want to tell you today is indeed a mystery story. And it's the best kind of mystery story, because we don't know who did it. I want to describe to you what is probably the biggest mystery in physics, the biggest puzzle, unsolved puzzle around. And just to let you know about it, and then maybe some of the young people here will get excited about that problem, and maybe one of you will solve it, because we desperately need some good ideas. So, when I was talking in New York City, I pointed out to people that these were stars. But here you probably get to see them every now and then. And in Cleveland, you don't get to see them very much either. But this is the night sky as it would look on a good night in the country. And it's beautiful. But what we've discovered in the last 15 years or so is that this is just the tip of a cosmic iceberg. That all the really important stuff, in fact, is not the stuff you can see, but the stuff you can't see. That the dominant and most significant stuff in the universe is the dark stuff between the stars. And you'll see that we're just beginning to learn how complex and interesting that space is, and the mysteries that it involves. So let's begin the mystery story. In 1915, it was a dark and stormy night, and Einstein had just developed, you heard he developed in 1905, 3 wonderful theories, but they paled in comparison to what he did in 1915. After 10 years of hard work, he had just developed the General Theory of Relativity, his greatest achievement. It was, for the first time in the history of physics, a theory not just of the motion of objects within space and time, but in fact could describe the dynamics of space and time themselves. It was a theory of gravity. And it was a theory that said the universe was far more interesting than we'd known before. In fact, space itself responded dynamically, as you'll see, to the presence of matter and energy in new ways. And because it was the first theory of not just how things moved in space and time, but how space and time themselves could evolve, it was, in principle, the first theory of the universe. With that theory, you could describe the origin, in principle, and evolution of the whole universe. And so Einstein applied it to that, or began to think about how to apply it to the universe, but there was a problem, a huge problem, in fact, because it didn't describe a universe that looked anything like the universe that Einstein lived in 1915. If you look out at the night sky, it appears static. The stars are just sitting there, nothing much is happening, and that's a big problem. That was a big problem for Einstein, because with general relativity, just like Newtonian gravity, all students who've taken physics know that gravity sucks. Okay? It always pulls. It doesn't push. And you've got this problem because if you put all these mass points out in a universe, they'll all attract each other gravitationally. And they won't be static. They won't sit there. Eventually, that whole system will collapse. It will collapse in Newtonian gravity, and it'll collapse in general relativity. And here was a universe that hadn't collapsed. And Einstein had this beautiful theory, which he knew had to be right. Yet it didn't describe the universe we lived in. Well, Einstein was no slouch, and he realized there was a way around that. So I want to talk a little bit about it. But first, you can't really do justice to Einstein without presenting Einstein's equations. So we've locked the doors, and I want to show you Einstein's equations here in a variety of forms. Just so you don't get too scared, I want to present them in a user-friendly fashion. Okay. So the left-hand side equals the right-hand side. Okay, we're okay with that? Okay. Now, that actually is not completely facetious. I wouldn't have done it if it was completely facetious. It's actually important because, in fact, Einstein's equations, the left-hand side represents the curvature of space, how space responds geometrically to the presence of matter and energy. And the right-hand side, in fact, represents the source of that curvature. And in fact, this is what makes Einstein's equation so interesting and at the same time complicated, because you see, matter and energy curve space, make space, change its structure, literally. But then in that curved space, that affects the motion of the matter that produces the curvature of space, and that changes the curvature again. And so there's this feedback, this nonlinear feedback that causes general relativity to be so interesting in one sense and complicated in another. So I wouldn't be a theoretical physicist if I wouldn't at least write down the Greek symbols just for you, although they may not mean much. But that's one way of writing Einstein's equation. But this is the important part. But what Einstein realized, and this is the equation that predicts that things should fall together, and you shouldn't have a static universe. And here Einstein had a static universe in 1915, and he tried to figure out what to do. Well, he realized that consistent with the mathematical symmetries that had led him to develop his theory, he could add an extra term to this equation. He could take the left-hand side and add an extra term. Now, what would the effect of that extra term be? Well, this term would produce a small repulsive force throughout empty space. It could be so small that you'd never notice it on the scale of the Earth or the solar system, which is pretty darn good because, of course, gravity works pretty well, and even Newtonian gravity in particular works very well on the scale of the solar system. So you better not have a lot of extra forces that can't be explained by Newtonian gravity. But even if it was very small on terrestrial or solar system scales, it could build up over the scale of galaxies and potentially, he hoped, hold apart distant objects against the gravitational attraction that would otherwise be present, and thereby result in a static universe. So that was his hope, and he called that term the cosmological term because it was there to have a cosmological effect, have an effect on the universe as a whole. Now, so he introduced it. However, shortly after introducing it, all sorts of problems arose. Not least of which, in fact, very shortly after introducing it, he realized, as other people did, that the universe wasn't static. In fact, when I was on leave a bunch of years ago in Switzerland, I went to a nearby university in Zurich and got a postcard from Einstein to Weil, who was a very famous mathematical physicist, written in 1923. And it said, my German isn't great, but it says, if you get rid of a quasi-static universe, then out goes the cosmological constant. What he meant by that was, well, already by 1923, people were realizing the universe wasn't static. In fact, it was expanding, as I'll get to in a moment. And if you have an expanding universe, you don't need a cosmological constant anymore. Because if the universe is expanding, gravity can be universally attractive again. And it can slow the expansion, and it could stop it if there's enough gravity and cause it to recollapse into a big crunch. Or it could just slow it down, maybe never stopping it. And that became, as you'll see, the business of cosmology for the rest of the 20th century, to try and figure out which universe we live in. But you didn't need this extra repulsive term. No longer did you need it. So Einstein said that was his biggest blunder. He wished he'd never introduced it. And we'll get back to that. But before we do, I want to say, okay, so the universe is expanding. Well, in 1923, there's some inklings of that by a bunch of people. But the person who really convinced the world that the universe was expanding was this guy here, Edwin Hubble. And Edwin Hubble, I like to talk about him because he gives me great faith in humanity. Because he started out life as a lawyer and became an astronomer. And so there's hope for everyone. And Hubble made a number of major discoveries as a young man, but the first one actually was not the fact that the universe was expanding, But in 1924, at the new Mount Wilson telescope, his first major discovery was that he looked with this big telescope, 100-inch telescope, he could see these things, what they were called nebulae. They're these little fuzzy things in our galaxy. And nebulae is sort of Greek for fuzzy thing. And then people didn't know what they were. There was a big debate about them. But he was able to show with the telescope that, in fact, these fuzzy things were not in our galaxy, not in our island universe, but in fact were other galaxies like our own, other island universes. And in fact, in 1924, we knew of, until he did that discovery, we knew of one universe, one galaxy in our universe, the Milky Way, the one we live in. We now know there are roughly 100 billion galaxies in the universe, in the visible universe. So you see, it's really a whole new field. Less than 100 years ago, 80 years ago, we knew of one, where we now know there are 100 billion. So everything's changing, and you're going to see that. And things have been changing dramatically in the last decade. So Hubble had already been well known by that point for making that profound discovery, but that was nothing compared to the next discovery he made, which is when you look out at distant galaxies, these what were former nebulae, look out at these distant galaxies, you see something really remarkable. As we look out, all of them on average are moving away from us. And something even more peculiar. If you look at galaxies that are twice as far away from us, they're moving away twice as fast. 3 times as far away from us, 3 times as fast. Okay? We codify that in the law, velocity proportional to distance. But it's very strange. We look out, everything is moving away from us, and the speed is proportional to its distance away from us. So what do you conclude from this? Well, you immediately conclude that we are the center of the universe. Okay? It's obvious. And unfortunately, as my wife reminds me on a daily basis, that's not the case. In fact, what this really tells us is the universe is expanding. Okay? Now, there are lots of different ways to try and, I used to try and explain this by talking, but I think pictures are much better. So how can you see that this fact that we appear to be at the center of the universe really means the universe itself is expanding? Well, the way to do that is to think outside the box. In fact, get outside the universe, which we can do when we, at least on a screen. So let's get outside the universe, and here's my simplified version of an expanding universe. Here's a bunch of galaxies at some time t1. You know, I put them a nice equal distance apart. And then a time t2 later, if the whole system is expanding, those galaxies are a little bit further apart. See? Okay? So that's what it would look like if you were standing outside of our universe. Okay? Stand outside, galaxies are moving. If the universe is expanding, they're all separating a little bit. Now, how would it look like if you're on one of those galaxies? So pick a galaxy. There's a galaxy. Okay? So if we want to see what it would look like at that galaxy, I just superimpose this image on top of this one, but placing that galaxy right on top of itself there. So we see the view from this galaxy, and you see everything is moving away from that galaxy. Okay? And it doesn't matter which galaxy you pick. Pick another galaxy. Same thing. Everywhere you are, the universe looks like it's moving away from you. So, I mean, depending whether you're an optimist or a pessimist, either every place is the center of the universe or no place is. Okay? But a uniformly expanding universe, it looks like that. And so what Hubble had really discovered, in fact, is this remarkable thing, that the universe is expanding. And it's changed our whole picture, of course, of nature, because an expanding universe had a beginning, already a profound implication that really was, in fact, quite new at the time. Now, it's so important, I just want to talk about how you measure it for the first few minutes, because it'll come back to haunt us later. So this is this law that velocity is proportional to distance. We call the constant of proportionality the Hubble constant, after Mr. Hubble. And the question is, how can you measure this? How can you determine this? Well, if you got this equation, you've got to measure velocity and then distance. So you look at a bunch of objects, you look at their distance away from you and measure their velocity. How do you do that? Well, the velocity is the easy part. To measure velocity, you use a phenomenon that you learn about in high school physics, hopefully, called the Doppler effect. In fact, there's an old slide I've got to get that I love. It's a cartoon by the cartoonist Sidney Harris. And it has these 2 cowboys sitting on a plane, you know, on horses looking out at a plane, and they see a train, and one of the cowboys says to the other, "I love listening to the lonesome wail of the train whistle as the magnitude of the frequency changes due to the Doppler effect." And what he was referring to is the famous fact that, in fact, if you have a train or ambulance or whatever coming towards you, the whistle, the noise, sounds higher. And if it's moving away, it sounds lower. The frequency is lower. And that's because when it's coming towards you, the sound waves get scrunched up. Their wavelengths get smaller. Smaller wavelength means higher frequency, means higher sound. When it's moving away from you, they get stretched out. Longer wavelengths means lower frequency, means lower sound. And the same thing happens for slightly different reasons to light. So that in fact, if objects are moving away from us, we can see the frequency of the light will be shifted by the time we see it compared to how it's emitted. And in fact, here's a schematic of that. So we look at stars, and they emit light. We know that. One of the most profoundly important things about the light emitted by stars is that it comes in a certain set of colors. A certain set of unique set of colors. And the amazing thing about that is that it's exactly the same set of colors that are emitted by hydrogen gas when you heat it up in the laboratory here on Earth. Heat up hydrogen, you get the same set of colors as you see from the stars. So what does that tell us? Two things. First, it tells us stars are made of hydrogen. Good. So it tells us the stuff of the universe that we can see is the same stuff as here on Earth. It's not so weird. But the other thing, and it's sort of not really relevant to the lecture, but I've got to tell you anyway because it's important to me. Because with my Star Trek hat on, I meet a lot of people who've been abducted by aliens, or think they have, or have friends who have. And I tell them, well, it probably isn't the case. Space travel is really difficult. And the laws of physics make it really virtually almost impossible to travel at the speed of light. And they tell me it's okay because the laws of physics are different on those stars than they are here and around those systems. But in fact, we can actually measure that the laws of physics are identical throughout the whole universe. It's not a hypothesis. We can measure it. How do we measure it? Well, we see the same spectrum of light emitted by these stars. And one of the great successes of 20th century physics was the explanation of the spectrum of hydrogen, the colors emitted by hydrogen. It was the basis of quantum mechanics. And in order for that explanation to work, we had to learn electromagnetism and quantum mechanics, two of the other pillars, other than relativity, of the 20th century. And so the fact that we see exactly the same set of colors in those stars means not just that they're made of the same stuff, but that the laws of electromagnetism and quantum mechanics that govern that spectrum here on Earth are identical out there. So it really tells us the laws of physics are the same. In fact, not only just across distance, but across time, as we'll see. In any case, we can use this fact. So if the star is not moving, it emits the same spectrum of light as on Earth. But if it's moving away, the wavelength's stretched out. The long wavelength end of the visible spectrum is red light. So we call it red shifted. If it's moving towards us, it's blue shifted. And we can, therefore, by the amount by which the wavelength of light is stretched, we can determine how fast it's moving. So that's the easy part. Okay? The hard part is to measure the distance to these objects. Velocity, proportional distance. How do you find the distance to distant objects? Okay? I mean, you don't have tape measures that are that long. Okay? How do you do it? Well, you could, in the old days when I was growing up, before they had lasers, surveyors used to tell the distance to the back of a room or a distant object by taking sightings and using parallax. I'd look at the back of the room there, I'd measure the angle there, and I'd walk a known distance over here, and measure the angle here, and then I'd use plane geometry to figure out the distance to the back of the room. Well, that only works for the nearest stars. Okay, you can only use that to see the distance to the nearest stars. To go further, you have to use something else. And another way I could tell the distance to the back of the room would be to turn on all the lights but one, and say I know I had a 100-watt light bulb shining in the back of the room. Okay? Then if I could find an old camera, like I used to have that at a light meter on it, I know there's a 100-watt light bulb there, and I'd take a reading over here, and I'd see how much power is coming to my camera. And I'd use the fact that the light spreads out, turns out to spread out, it's 1 over the square of the distance from me to the light bulb. And I'd see how much power I'm receiving here, and if I knew it was 100 watts there, and I received a certain wattage of light here, I'd be able to work out how far away the light bulb was. Okay? So that'd be great if the universe was populated by 100-watt light bulbs. We'd have no problems. It's not. So we have to find the equivalent. We have to find what we call a standard candle. Okay? Something whose intrinsic brightness we know, we believe we know, and then we look at how bright it appears, or how dim it may appear, and from that we determine how far away it is. Okay? And that's the hard part, and that's why it was very difficult to measure this. In fact, I have Hubble's data here from 1929, where he measured velocity and distance to distant galaxies, he thought. And this is one of the reasons why he was such a great scientist, by the way, because he knew to draw a straight line through this data set, because it's not at all clear that that's an appropriate thing to do. But he did it. And then when he did it, he got this relationship, velocity proportional distance. The only problem is he got it wrong by a factor of 10 compared to what we know the answer is today, setting a noble tradition in astrophysics. It's okay. I mean, it was very difficult to do. It's actually, at the time, I should point out, caused problems. And in the present time, it's probably worth mentioning these, because it turns out if the universe is expanding a lot faster, this is 10 times faster almost than we think the universe is actually expanding, then you can work it out that the universe is about 10 times younger, because it takes less time for the galaxies to get out where they are now. They all started at the same point. And you work it out, the age of the universe for this value would be something like 1.5 billion years old. And that was a problem back in 1929, because even in 1929, except for places like Tennessee and Ohio and Georgia, we knew the Earth was at least 3 billion years old, okay? And as I say, we still do. We know it's 4.5 billion years old now. So it was a problem that the Earth was older than the universe, okay? And it caused a lot of problems at the time. Of course, now we know why, because he got the number wrong. But we want to do better. It's been 80 years, and we try to do better. And the way to do better is to get better standard candles. And here's a picture with the Hubble Space Telescope. Beautiful device, which we wish would stay up a little bit longer, and maybe we can convince the government to do that. It's not so clear. But it's done a wonderful job. And one of the reasons the Hubble Space Telescope is called the Hubble Space Telescope is not just to honor Mr. Hubble, which is a nice thing to do, but because it was really designed to measure the Hubble constant. Because one of the things that the Hubble Space Telescope could do, here's a distant galaxy, is we could get a close-up of that distant galaxy with the Hubble Space Telescope, and for the first time with any such telescope, have a resolution so that you could see individual stars in those galaxies. Now, what does that matter? Well, there's a certain type of star called a Cepheid variable star. It's a variable star. It varies brightness over a period of days or weeks. And one of the things that was discovered, we can measure such stars in our galaxy, they're relatively close by, where you can determine their distance independently, is an amazing relationship. That there's a relationship between the brightness of those stars and the period with which they vary. And so therefore, if you look at one of those stars and you see how long it takes it to vary, you immediately know its brightness. Now you see, if you could look at those stars in a distant galaxy, see how long it takes them to vary, you'd know how bright they were, and then you could see how bright they appeared, and then you'd know how far away the galaxy is, and that would give you that distance piece, and you'd measure the Hubble constant. So these are Cepheid variable stars in this galaxy. We're in the box here. And you could try and determine the distance to this galaxy, which is relatively nearby. But to do a better job, you want to measure faraway galaxies, and you can't see individual stars in faraway galaxies, so you have to find a new kind of standard candle that's even brighter. And in the last 10 years, we found a new standard candle. This is one of my other favorite Hubble Space Telescope pictures. Actually, every picture from the Hubble Space Telescope is my favorite. And I like this one because it looks like a painting to me. But it is, in fact, a galaxy far, far away, long, long ago. And it's a spiral galaxy, much like our own. Once you've seen one, you've seen them all, more or less. And this object here, this looks like a nearby star, okay? But it's not. It's a star right on the edge of that galaxy. But it's as bright as the whole darn galaxy in the center. How can that be, that an individual star would be that bright? Well, this is a star that's just exploded. It's a supernova. It's a star that has exploded, and exploding stars produce a brightness for a few weeks as bright as a whole galaxy. Now, how often do stars like this explode? About once every 100 years per galaxy, a star explodes, forming a supernova, the brightest fireworks display in the universe, essentially. So, if you want, it turns out, as you'll see, these are wonderful standard candles we've just discovered. But if you want to use them, they happen once every 100 years per galaxy. That's kind of rare. But there's another great thing about the universe. It's big and it's old. And therefore, rare events happen all the time. And so, one way you could do this is you could assign, so once per 100 years per galaxy. Okay, so all you have to do is assign a graduate student to each galaxy. Then you got, 100 years, that's about the average time for a PhD. And they're dispensable anyway. So, but that's one way. Another way that's much better is to realize that if you look far enough, you'll see a lot of galaxies. And it turns out if you look very far, in a small region of the sky about that big on your eye, you'll be able to see maybe about 100,000 galaxies. And if you could look at 100,000 galaxies in a single night in a small region of the sky, well, the laws of probability say if there's once every 100 years per galaxy, that roughly you'll find out you'll get about 10 exploding stars every night. So it's really amazing. Astronomers go out and they do a proposal saying, I want to use this telescope to look, and tonight I'm going to see 10 exploding stars. And it's amazing. They do. Well, some nights they see 9, some nights 11, some nights it's cloudy. But it's amazing. And that means we can use these objects to probe the universe. And here's for example, how it's done. You take an image. This is a deep image. Every spot on this picture, except for this, and this, are in fact galaxies, not stars. Each galaxy containing 100 billion stars, roughly. They're all over the place. And you look at all these objects, and you look at them again a few weeks later, and then you compare the brightness. And in this particular galaxy, if you blow it up, this is how it looked 3 weeks before. This is how it looked on that day. You subtract those two images, and you see something left over. And that thing that's left over is the change in brightness of that galaxy, and that's a supernova. And in fact, we can do better. I gave a little movie. Here's a galaxy with an exploding star in it. Okay? We can look at it visually. We can measure its brightness as a function of time. When this will repeat itself, there it goes, gets brighter. We can look at the set of colors emitted by that star as it explodes. And that tells us that set of colors is like a fingerprint. It tells us it's a certain type of supernova called a type 1a supernova. It doesn't matter why it's called a type 1a. That's what it's called. But turns out these type 1a supernovae are great standard candles because of an amazing accident that we still don't really understand. If one looks at the brightness, this is the brightest day of each supernova. When it's maximum brightness, we call that day 0. This is 20 days before that and 20 days after it, 40 days. So you see the supernovae get bright and dark over, of course, about a month or so. But the brighter supernovae stay brighter longer. And it is an amazing fact, experimental or observational fact that we still don't understand, that the brighter supernovae stay brighter longer in an exact relationship to their brightness. Namely, if I divide each of these curves by the brightness, all of those curves fall on exactly the same line. Telling us that if we look at a supernova and see how long it's bright, we know how bright it is. And if we know how bright it is, we got a standard candle. But not just a standard candle that you can see nearby, a standard candle you can see billions of light years away, and thereby measure the universe as it's evolving, as it looked a few billion years ago and today. And so supernovae have been great to measure the Hubble constant. Here's a modern Hubble curve. See, it looks more like a straight line than Hubble's, but there's one real reason for that. That's what we've discovered, the miracle of log-log plots, which make everything a straight line. But in spite of that little bit of magic, it turns out we can now use these things to measure the Hubble constant to an accuracy of about 10%, which is 80 years of hard work. And hopefully before the end of the lecture, you will understand why. Now, I should stop at this point and say, I want you to think back at those pictures of those stars I showed you at the beginning. Okay? My purpose today will be to make you dizzy. Okay? I'm going to throw a lot of stuff at you. And in the end, you're going to see that our picture of the universe has changed dramatically. And you might not remember all the details. But at the very least, I hope that next time you look up at the night sky, you have a different perspective of where you're coming from, because that's the way we are. In any case, the universe is we now have definitively measured the universe expanding. And in fact, we know the expansion rate. The Big Bang really happened. There's no debates. But let's get back to Mr. Einstein, 1915. He said, okay, well, the universe is expanding now, 1929. Damn it. I wish I'd never introduced that thing. Let me get rid of it. But unfortunately, it's kind of like putting the toothpaste back in the tube. Okay? Once you get it out, it's hard to get it back in. And we now realize that even if Einstein hadn't introduced the cosmological constant in 1915 or 16, someone else would have, because we now think of it very differently than he did. We do that because of the miracle of modern mathematics. With the miracle of modern mathematics, I can rewrite that equation, okay, in this form. Now, That's a small step for a mathematician, but a giant leap for a physicist. Because, in fact, the point is that when I take this term and put it on this side of the equation, mathematically it's trivial to do that. But now remember, the right-hand side of Einstein's equation means something very different than the left-hand side. When I put that term on the right-hand side, it suddenly has a new significance. It suddenly looks like a new type of form of energy in the universe. What could give an energy that looked like that? And it turns out there's one and only one thing in general, and that's the energy of nothing. Now, by this I don't mean the energy of nothing. I mean the energy of nothing. I mean, if I take space and get rid of everything, get rid of all the particles and the radiation and everything, and just have empty space, if I give empty space energy, then it will produce a cosmological constant. Now, this is absurd. Okay, because, you know, empty space is empty. I mean, if I asked, let's say I asked George Bush. Okay, no, let's say I asked a 4-year-old, okay? What's the energy of empty space? Then they'd say nothing, right? Because there's nothing there. It's the only sensible answer. And it is the only sensible answer, except we now realize that empty space is not empty. Empty space, we now realize, is a boiling, bubbling brew of virtual particles that pop in and out of existence on a time so short that we can't measure them directly. Due to the laws of quantum mechanics combined with relativity, in fact, with Einstein's relativity, the two together imply there must be these particles that pop in and out of existence on a time scale so short we can't see them, which sounds like counting the number of angels on the head of a pin, right? I mean, it sounds, what's the point of inventing particles you can't see? Theorists are just playing. Well, the point is you can't see virtual particles directly, but you can actually measure them indirectly, which is how we know it's right. Here's how. Here's an atom, a hydrogen atom. There's a proton, center, and an electron orbiting around it. It was one of the great successes of quantum mechanics, the Bohr atom, that we understood the colors of light emitted by hydrogen because the electron could jump between energy levels, and when it absorbed or emitted light, that's the colors of the spectrum. So great, quantum mechanics predicted those energy levels. But in fact, it didn't predict them right. Roughly it predicted them right, but when we measure them very, very carefully, we find out that we get the wrong answer. Because this isn't what a hydrogen atom looks like. We have to remember that there are virtual particles and antiparticles that can pop in and out of existence. So if I think of time in some sense going in that direction, I create a particle-antiparticle pair, an electron, say, and its antiparticle, a positron, at some instant. Now, the electron is going to like to hang around for while it exists, but near the proton, because it's attracted. The positron is going to be repelled, and then the two are going to hang around, then annihilate again, and they're gone poof. But while they're there, they're going to change very slightly the charge distribution of a hydrogen atom. And the neat thing is they do it in a way we can calculate. And when we see how they change the spectrum, they produce the best measured prediction in all of physics, in fact, in all of science. If I can calculate now, using this extra effect, the difference in energy levels that electrons jump to, the predicted difference compared to the observed difference divided by the predicted difference is better than 1 part in a billion. The prediction agrees with observation better than 1 part in a billion. It's the best measured prediction in all of physics, as I say. There's nowhere else in science that you can make a better prediction. Telling us that these particles, virtual though they are, have an indirect impact that we can measure, and we know that they're there. And we know that empty space ain't so empty. Okay? Now, in fact, there are other observations you can do. A Dutch physicist named Casimir realized that another impact, if you took 2 parallel plates of metal very close together, the virtual particles that appear outside the plates are different than the ones that appear inside. And in fact, that produces a force that pushes the plates together a very little bit. And if you do a very careful experiment, like this experiment between parallel plates, it's just a tabletop experiment. But you can set it up, measure it, and you find the force is exactly what we predict if virtual particles are there. So there's no doubt about it. The virtual particles are there. We're comfortable with that. Now, however, we can ask the question, what does that do to the energy of empty space? If empty space isn't so empty, we can calculate the energy of empty space. Right? And we do the calculation. And we got a problem. We calculate that the energy of empty space is roughly a gazillion times the energy of everything we see in the universe. That's a problem. Okay? Turns out to be a huge problem because we wouldn't be here if that were true. In fact, we know, for reasons I'll show you, that the energy of empty space can't be much more than the energy of all the matter we see. So, in fact, our prediction is 120 orders of magnitude wrong. And it is, without a doubt, the worst prediction in all of physics. Okay? I mean, I may have made worse predictions, but I'm not sure I published them. Okay, so that's why we never talked about it. Okay? But we knew it was there. It's this problem that's become known as the cosmological constant problem. We predict with the same theory that does a great job with atoms, we predict what the energy of empty space should be, and we come up with an absurd result. How can we solve this? Well, theoretically, and this is the way it's been done since I've been a graduate student, we knew what the only solution is. Look, there's no way we could, if we know that this number can't be much bigger than this number, and we predict it to be a number that's 120 orders of magnitude bigger, we're not going to have some effect that's going to cancel things out and leave something left over of order this magnitude. That's going to cancel out everything down to the 120th decimal place and leave something finite left over. That just seems absurd. But mathematically, something that's less absurd is to say, well, the number's 0. Maybe there's some new symmetry of nature that we don't know about that causes all of the virtual particles to cancel out exactly. Now that's sensible. 0 is a sensible number. 10 to the minus 120 isn't. So we figured, theorists figured, that the number must be 0. Okay? That there's some symmetry in nature we haven't figured out yet, but it makes the energy of empty space exactly what a sensible energy of empty space should be, precisely 0. So people like me could go to sleep at night and not worry about it. Okay? And we said, okay, someday someone's going to solve that problem. That's one reason why we knew the energy of empty space was 0. But there's another reason. It's called the coincidence problem. And the coincidence problem is the following. This is a graphical way of presenting something that you should understand without the graph pretty easily. But in any case, that is that as the universe expands, the density of matter goes down. It goes down as 1 over the volume. There's less stuff per unit volume. And that's all that this curve shows. It shows the density of matter going down on a peculiar scale as the universe expands. So we know the universe is getting less dense. But what about the energy of empty space? If I put energy in empty space, what does that energy do? Well, it turns out that the equations of general relativity tell us what it does. The energy of empty space remains constant as the universe expands. It's peculiar, but it does. Heuristically, here's the reason why I can think of this. Well, empty space is empty, and therefore there's nothing to get diluted as the universe expands. Okay? It sounds like a card game, but it's true. It works out, that's what the equations tell us. That empty space, the energy of empty space, if it's there, it remains constant. So, you notice, however, that implies something weird. These two intersect at one and only one time. And let us say that the energy of empty space today is comparable to the energy of matter. Well, that will be the only time in the history of the universe when that's true. For all earlier times, the energy of matter would be much greater, and for all later times, the energy of empty space would be much greater. So why should we, living at this random time 15 billion years after the Big Bang, be living in the only era in the history of the universe when the two are comparable? It's absurd. Well, the only way to get rid of that problem is to say the energy of empty space is 0, so there's no intersection at all. So you don't have to worry about any such coincidences. So every theoretical argument, from fundamental physics perspective, from astronomical and cosmological arguments, tells us we know the energy of empty space is 0. But the great thing about cosmology, and in fact physics, is that it's an empirical science, something a number of my colleagues lately have been forgetting. It's empirical. If you want to see if it's at 0, you better measure it. It's not just good enough to say it. It's not philosophy, it's physics. Okay? So we got to measure the energy of empty space. How can you do that? Well, the first person to tell us how to do that was, in fact, in my opinion, George Orwell, who said, to see what is in front of one's nose requires a constant struggle. What did he mean by that? Well, look at the end of your nose. You can see it. Most of us can anyway. Okay? Well, that's quite significant if you think about it, because remember what a cosmological constant would do, an energy of empty space would do. It would produce a small repulsive force. And that repulsive force would cause things to move away, cause, in fact, space to move away, to expand. And the velocity of objects would be proportional to their distance away from us. That constant proportionality would be a constant for all time. And what that means is objects, as they got further away from us, would be moving faster and faster and faster, and eventually their speed would exceed the speed of light. Now you might say, I've learned in school that nothing can exceed the speed of light, and that's a lie. We lie to you when we say that. Okay? Well, we don't lie. You have to be more like a lawyer and parse it a little more carefully. Okay? Nothing can travel through space faster than the speed of light. But space itself can do whatever the heck it wants, as far as we know in general relativity. And it can carry things away from us at the speed of light or greater. In their rest frame, they can be at rest, but they're being carried away with space, by space faster than the speed of light. When that's the case, they disappear from our world, in a sense, because if they're moving away faster than the speed of light, then the light emitted by those things can never catch up, and it never comes to us. So look at the end of your nose. The fact that you can see the end of your nose, it's a wonderful experiment. It doesn't cost anything. The fact that you can see the end of your nose already tells us that the energy of empty space is 60 orders of magnitude smaller than that prediction I presented up there. So we already know the prediction is nonsense. Just the fact that you can see the end of your nose tells you the energy of empty space must be much smaller than that naive prediction. But of course it tells us, unfortunately, why we need astrophysics and not laboratory physics to measure the energy of empty space. Because in the laboratory I can see to the end of my nose or to the end of the room, or CBAF I can see in a big room the end of the room. But with astronomy and cosmology I can see galaxies the other end of the visible universe. The very fact that I can see those galaxies tells us that the energy of empty space cannot be much bigger than the energy of all matter. And that's where you get that fact that the energy of empty space is at least 120 orders of magnitude smaller than that naive prediction. But it tells us if we want to be sensitive to that energy, we're not likely ever going to be able to do a laboratory experiment. We've got to do astronomical experiments to look for it. We've got to weigh the whole universe to determine the energy of the universe. So how do you weigh the universe? Well, you stand on the shoulders of giants. Okay? I don't know if anyone knows who this is. He's a guy, I took this picture myself. It's an island off Sweden. It's a Swedish island. Now it used to be a Danish island. It was given to this guy by the King of Denmark at the time. If you look very carefully, he's missing the end of his nose. The name is Tycho Brahe. He was a great astronomer who was given this island because he saw an exploding star, actually. And it was such a neat thing. It's an exploding star in our galaxy. The king gave him this island. And he spent 20 years of his life doing one thing. Before the invention of the telescope, by the way, he basically carefully measured the position of the planets in the sky every night. That's it. That's all he did. He took the data, measured it. That's what he did. He got kicked off this island because the king changed and he was a crummy feudal lord. He moved to Prague, and he got not a hapless, but an unfortunate young man at the time named Johannes Kepler. And he said to him, before he died, he said, figure this out. What does this mean? And Kepler spent the better part of his life, without a Macintosh or any other kind of computer, working out what it meant, all that data meant. And he came up with what we now know as Kepler's laws. And there's lots of different ways of presenting them, but this is the best way of presenting Kepler's laws. The key law of Kepler is that if you measure the velocity of planets around the sun as a function of their distance from the sun, there's a relationship. The detail is not that important. If the square of the velocity goes down as 1 over the distance, that doesn't matter so much. There's this wonderful relationship. And to prove it, I did what, the only way you can get these numbers are look at a first-year astronomy textbook, so I got those numbers out of that. I plotted a 1 over r law there for 1 over square root of r law, and you see it fits perfectly. I mean, I would have fudged the data if I had to, but I didn't. Okay? It's amazing. Now, what did that do? Well, that made Newton rich and famous, Isaac Newton, because he realized that if you could explain Kepler's laws, if you had a theory of gravity, his theory of gravity, which said that there was a specific relationship, a force law between massive objects that went like this, which is Newtonian gravity, because it makes the prediction that the square of the velocity of planets should fall off with 1 over distance, but the constant of proportionality should be a constant, okay? So v squared should go like 1 over r. It explains Kepler's laws, and it actually tells you what the constant of proportionality is. It's the strength of gravity, g, times the mass of the sun, m. But Newton didn't know the strength of gravity. He couldn't measure the strength of gravity because gravity is the weakest force in all of nature. Something you don't think about when you get up in the morning, okay? But it turns out gravity is much weaker than all other forces. And if I had more time, I'd give you a wonderful example of Richard Feynman's for that. But I think I'm not going to. You can ask me afterwards for Feynman's wonderful example. But gravity is so weak, it's very difficult to measure. It took 100 years before we could measure the strength of gravity between reasonable-sized objects. A guy named Cavendish did it in 1798. And he created another wonderful precedent, or at least he's the first example I know of it. When I was at Harvard as a young postdoc, I learned something very important. At least I thought it was new. That is, if you want people to read your papers, your scientific papers, you got to come up with a sexy title. Okay? And I thought that was a great new discovery, but I realized later that it went back all the way to Cavendish, because Cavendish, when he measured the strength of gravity, his paper wasn't called On Measuring the Strength of Gravity. His paper was called Weighing the Earth. Much sexier. Okay? Why? Because, well, he realized we know the velocity of the moon around the Earth, we know its distance, and if he could measure g, then he was the first person in history to know the mass of the Earth. Now, if it worked for the Earth, it could work for the sun. Let's use Kepler's laws to weigh the sun. And we can do that, in fact, by fitting, this is a curve that goes down like 1 over the square root of r. And if the sun were heavier, the curve would be up here. If the sun were lighter, the curve would be down there. So by fitting this curve, we can determine the mass of the sun. And this is the way we measure the mass of the sun now. It's how we know how heavy it is, by fitting it to that curve. And the fit is so good that in principle, we know the mass of the sun to better than 1 part in a million. We don't, in fact. We don't because we don't know g that well. It's the worst measured constant in nature. We only know it to slightly better than 1 part in 10,000. So that's our limitation on our ability to know the mass of the sun. Okay? Now, in physics is just like Hollywood. Okay? If it works, you copy it. Okay? And you keep on copying it. Work for the Earth, work for the sun. Let's use it to weigh the galaxy. Okay? Here's a galaxy. Again, it's not our own galaxy. Why? Why isn't it our own galaxy? I want to see if you're still awake. Yeah, we live in our own galaxy, so we can't see it from the outside that far. This is the Andromeda galaxy. It's the nearest large galaxy to our own. And if this were our galaxy, we'd kind of be living in a boring suburb right around there. I don't mean where we are right now. I meant where the sun is. It is right at the edge of the galaxy. And our sun goes around our galaxy about once every 200 million years. It orbits around our galaxy. And there you go. You see, it's at the edge of our galaxy. It's being pulled by gravity. You can use Newton's laws to weigh the galaxy. Okay? And before I do that, we actually can see our galaxy now. Most of our galaxy is obscured by dust. So with a telescope at night, you can't see most of it. You can see the Milky Way a little bit. But in fact, if you go above the Earth's atmosphere and use radio frequency radiation, microwaves, and infrared radiation, you can actually take a picture of what our galaxy looks like. And this is our galaxy as seen from where we are. It's a picture taken in 1989 or so by the Cosmic Background Explorer satellite. So as promised, we live in a spiral galaxy. We're looking edge on, and we're right at the outside of it. That's our own galaxy. Okay, but having seen that, we can say, how fast is the sun moving? It's moving at some speed. How far away is it from the center of the galaxy? Turns out about 25,000 light years. Plug those two numbers in at speed and distance, and you measure the mass of the galaxy inside the orbit of the sun, and that's 100 billion solar masses. And when you do that, you jump up and down with excitement. Because, in fact, if you count the number of stars in our galaxy, you find out that they're roughly 100 billion. So everything works perfectly. The mass of the galaxy is 100 billion times the mass of the sun. The number of stars is 100 billion. Everything holds well. But let's do better. Let's measure this curve at other points so we can fit it better and know the mass better. So look for objects that are further away from the center of the galaxy than we are. And when we do that, a problem arises. You don't have to be a scientist to realize that this data does not fit this curve very well. Okay? In fact, instead of falling off as it's supposed to, the velocity, we look at globular clusters, large magellanic clouds and stuff, satellite galaxies, out to distances 10 times as far away from the center of the galaxy as our sun is. And instead of the velocity falling off like it's supposed to, it's constant. What the heck is happening? Well, the only way you can understand this, if gravity works, is if there's more mass pulling these things in. In fact, if the mass of our galaxy increases with distance linearly, then you can explain this flat curve here. And that would mean, since we go out to 10 times as far from the center of the galaxy as we are, there's 10 times as much mass out here as there is in here. But we're at the edge of our galaxy. There's nothing out there that we can see. And this was the first evidence that, in fact, our own galaxy is dominated by what physicists colorfully call dark matter. Not very colorfully, perhaps. It's stuff that doesn't shine. Somehow the dominant stuff in our galaxy is stuff we can't see. Now, whenever you see something like this, the first thing you should do, especially if it's in the newspaper, is you shouldn't believe it. Okay? Because most observations are wrong. Most experiments are wrong the first time they're done. So you should repeat it. And in this case, however, when we repeat it, here's another galaxy, the flat rotation curve. If we look at all spiral galaxies, essentially, instead of the velocities falling off there like they're supposed to, they're constant for all of them. Telling us that not only our galaxy, but all galaxies appear to be dominated by this dark matter. Most of the mass in the universe is invisible. And that means if we want to weigh the universe, we've got to concern ourselves with how much of that mass there is. Okay? Now, why do you care how much mass there is again? Well, we not only do we want to know about the cosmological constant, we want to know the future. And one of the reasons you come to lectures like this is so you go to a cocktail party later and you can say some of the stuff. You know, it sounds good. And this is the cocktail party slide, because it sounds good. So if general relativity tells us that the geometry of the universe responds to matter. And that means the geometry of the universe can be of one of three types: open, closed, or flat. What does that mean? Well, I mean, here's a two-dimensional picture. So I can't draw a curved three-dimensional universes very well. But a closed universe, if it's dominated by matter, will in fact expand and then collapse. Okay, in a big crunch, the reverse of the Big Bang. An open universe, if it's dominated by matter, will go on expanding forever. And a flat universe is just the boundary between which will almost collapse but never quite collapse. So you see, we want to know how much stuff there is because it determines the geometry of the universe, because it determines the future. And in fact, that's why I got into cosmology 20, 30 years ago. Because I realized that if I could figure out how much dark matter there was, then I would be the first person in the history of humanity that could tell us the future of the universe. I'd know it, and I'd be the first person to know how the universe would end. So that's why I wanted to study this field. Okay? So we want to know how much dark matter there is, and there's lots of it in our galaxy, but clearly we have to know if there's stuff on scales bigger than our galaxy. Now, it turns out I want to give you a homework assignment. Okay? Not only did I give you equations, but I'm giving you homework. Okay? You too can determine exactly whether the universe is going to end or not, simply with high school physics. You don't need to know any general relativity. High school physics. Because if I take a coin, which I may or may not have in my pocket, and I do, and I throw it up, it comes back down. Okay? If I throw it up faster, it goes up higher. It takes longer to come back down. If I throw it up really fast and there's no ceiling, it doesn't come down at all. How do I determine that? How does NASA determine that? Well, they use high school physics. Some of you, this will bring back bad memories, other ones not, but it doesn't matter what these terms are, but the total energy of something when I throw it up has two pieces. It has a positive piece, we call it kinetic energy, which depends on its velocity, and a negative piece due to the gravitational attraction of the Earth. And all that matters is, it turns out if the sum of these is positive, if this term is bigger than that term, the object will escape. If this term is smaller than that term, the object will fall down. And that's how we determine the escape velocity of the Earth. It's simple. When this term beats that term, when the velocity is big enough, the object will escape. Well, it turns out we can do that for the whole universe, and here's the homework assignment. Get a telescope. Remember, we're here and galaxies are moving away from us, and so the Hubble constant tells us how fast a galaxy at a certain distance is moving away from us. So let's look at that galaxy, and let's look at its total energy. It's got the positive piece due to the Hubble constant. So go out with your telescope and measure the Hubble constant in your backyard, okay? That's the positive piece. Then all you have to do is somehow determine all the mass inside the orbit of that galaxy, or the distance of that galaxy from us. And that will give us the negative piece. And then you compare the two. And you see, this is much harder because it depends on mass, which you don't measure. You measure light, and you have to infer the amount of dark matter. But if this term is bigger than that term, if b over a is bigger than 1, negative is bigger than positive, the universe will collapse if it's dominated by matter. If b over a is less than 1, it will expand forever. So you can determine that exactly by high school physics. And whenever you get a ratio that's really important in physics, you give it a Greek letter. So we call it omega, the Greek letter omega. And the business of cosmology and astrophysics largely in the 20th century was to measure omega. That was it. Measure omega and you know the future. To measure omega, you got to know this. You got to know how much dark matter there is. Well, how much dark matter is there between galaxies? Now we're getting to the last 10 years, and you'll be pleased to know we're very close to the end of the lecture. The last 10 years where everything has changed. Here's another of my favorite Hubble Space Telescope pictures. I like it because, again, everything in this picture is a galaxy. It's just amazing to think in each of those island universes there may be stars with planets around them and life, and each of those, for the people or things on those galaxies, that's the center of the universe. And there are lots of them. In any case, we want to know how much mass there is between the galaxies, not just in the galaxies. How on earth could we measure that? There are lots of ways, but my favorite way is also due to Mr. Einstein. Since this is Einstein's year, let's talk about it. It's a picture. This is a picture where, again, every one of these dots is a galaxy. Several billion light years away, in fact. But you notice that there's something strange about this picture. There's some dots that look different than the others. There's a lot of blue things. Okay? Well, what that is a phenomenon that Einstein predicted in 1936. But he said we'd never measure it because he underestimated observers. He realized that light bends due to gravity. And if you have a big enough mass, it'll bend light around it and it will act like a lens, just like your glasses. And if it's a lens, it can magnify things behind it, but it can also produce multiple images of things behind it. And we now know from this observation that in fact all of these blue things are in fact many images of a single galaxy that's located about 3 or 4 billion light years behind this cluster of galaxies. And the multiple images are formed by the mass of this whole system. Now you see we understand general relativity, so we can work backwards. And from this image, we can determine how much mass there is in the system and where it's distributed. So we work backwards, and here's a picture of where the mass is in that cluster of galaxies. Now this clusters of galaxies are the biggest bound objects in the universe, tens of millions of light years across. Anything that can fall into anything due to gravity will fall into them. So if we can weigh these, they're the biggest objects in the universe, we can determine how much total matter there is in the universe. And we weigh it so we see there's spikes where the galaxies are. There's a lot of dark matter between the galaxies. And we now know, and this is only about 9 years old, this determination, maybe less, probably 8 years old, unambiguously, that when we add up all the matter there is in the galaxy, in the universe, including dark matter, we only get 30% of the amount of mass needed to close the universe, or to make it flat. Apparently, we've discovered in this way that the universe is open. It will expand forever. It's full of mass. Okay? It's not closed. It's not flat. Now, this was a huge problem, because you see, theorists like me knew the answer. We didn't need the observers to tell us. Okay? We knew that the universe is flat, because the only mathematically beautiful universe, it turns out, is a flat universe. So we were convinced. And this was a huge problem. Okay? Now, it turns out if there's a problem like this, why not try to do something else? Instead of just weighing the universe, let's measure the geometry of the universe directly. And what is amazing is in the last 5 or 7 years, we can measure the geometry of the universe directly. How? Well, here's a problem. How would you measure the curvature of the Earth if you couldn't go around it and you couldn't stand in space and look at it? Okay? Well, here's how. Take a triangle. What's the sum of the angles in the triangle? I should ask the high school students. Okay. Well, as any European high school student will tell you, it's 180 degrees. Okay? Now, but that's okay. That's because Euclid told us that. But if it turns out to not be true, if I take a circle or sphere. On a sphere, if I draw a triangle, I can make it add up to something very different. Let's go along the equator, okay? Then make a right angle and go up to the North Pole, and then make another right angle and go back down to the equator. And now you see I have 3 right angles, and 3 right angles adds up to 270 degrees. So you see on the surface of the Earth, a 2-dimensional curved object, I could measure the geometry of the Earth by measuring the angles of a triangle and see if it's curved. So let's try and do that for the universe. Find a triangle in a sense that we can measure. And it turns out we have that triangle. And only very recently have we been able to see it, using one of the most amazing things in cosmology, the last little bit of the puzzle that I'm going to put together for you. The cosmic microwave background radiation, the afterglow of the Big Bang. It turns out that indeed, if there was a Big Bang, there should be an afterglow. And here's the reason. We're sitting on Earth. We're looking out. When we look at galaxies a billion light years away, we're looking at them as they looked a billion years ago. It's cosmic archaeology. It's amazing. The further out we look, the further back in time we're looking. So that would mean if you looked out 15 billion light years away, you'd be looking back, if the universe is 15 billion years old, you'd be looking back at the Big Bang. So we should see the Big Bang. The problem is we can't, because between us and the Big Bang there's a wall. Not a physical wall, but a metaphorical wall. And here's the reason why. As we look back in time, we're looking at an earlier and earlier universe. And the universe was hotter and hotter and hotter at early times. And when the universe was about 100,000 years old, it was about 3,000 degrees in temperature. And it turns out at that temperature, hydrogen, which is the dominant stuff in the universe, gets knocked apart. Electrons get knocked out of hydrogen by the radiation. When they kind of recombine, they get knocked out again. So instead of neutral matter, you've got this ionized plasma of stuff. And that's opaque to radiation. You can't see through it. So it's just like this wall. I can't see past this wall because it's opaque. So if I look out, I can't see past that wall. And if I run the film forward, in a sense, as the universe is getting cooler and cooler and cooler, finally it reaches a point where the hydrogen can combine, become neutral, and then the universe becomes transparent. And I would expect to see the radiation from that surface just like I see the radiation from this wall being absorbed from these lights and re-emitted. I would expect to see a bath of radiation coming at me from that surface. And that's not at a temperature of 3,000 degrees, but the universe has cooled since then. That radiation will have cooled. I should expect to see it at 3 degrees. And that was the radiation that was discovered by accident in New Jersey, of all places, in 1965 by two guys at Bell Labs who didn't know what they were doing, but except they won the Nobel Prize for doing it. Because they got a picture of what the universe looked like when it was 100,000 years old. And there's one aspect of that picture that we now have that's important, that we couldn't have gotten then. Turns out there's one scale on that picture that we really care about. It's a degree across. Why a degree? Because that's 300,000 light years in distance on that surface. And if the universe was 300,000 years old, then light can't have traveled more than 300,000 light years. And that means since information can't propagate faster than the speed of light, nothing that happens here on that surface could have affected anything that happened here at the time that surface was created. This region didn't know about that region. And if there's a big lump here, if there's a little lump, it knows it's a lump, and it can collapse, and pressure can respond, and all this stuff. But if it's a big lump, it doesn't even know it's a lump. It can't even begin to collapse. And so this scale should differentiate regions where microphysics can respond to macrophysics from regions where it can't. So we would expect to see a signature of stuff collapsing and stuff an order a degree across. So let's take a picture of the microwave background on that scale. If we do, we can measure the geometry of the universe. Because here we have a ruler that's 300,000 light years across, a known distance away from us. We can calculate the angular size of that region. And we turn out it's a degree. It's a degree if the universe is flat. But if the universe is curved, then light rays curve. And if it's open, turns out light rays diverge as you go back in time. If it's closed, light rays converge. And you see the angle on our eye, spanned by the same length surface, will be different. Not a degree, but half a degree or 2 degrees, depending upon whether the universe is curved. So just by looking for those lumps and saying, how big do they look, we can measure the geometry of the universe. Let's measure the lumps. In 1998, this experiment was launched, the boomerang experiment in Antarctica. It was a balloon to go above the Earth's atmosphere. You can measure this radiation with a microwave radiometer on it. And it was sent around the world, which is easy to do in Antarctica. It's at the South Pole, it's really easy. But this one took about 2 weeks to go around, and it looked at a little region of the sky and measured that radiation and took a picture. And here's the picture. Well, I've superimposed the picture with the original image because to me it's a wonderful visualization of our cosmic myopia. We're used to the fact that it's bright during the day, light during the day, and dark at night. But that's only because our eyes are sensitive to visible radiation. If our eyes were sensitive to microwave radiation, then day or night we'd be looking out and we'd see that surface 15 billion light years away. And here are the hot spots and the cold spots in this surface. And we can ask, how big are they across? Are they 1 degree on average, smaller than 1 degree, or bigger? And here's another way to do it, a different false color version of this image. And here are some universes on a computer that you create. With 300,000 light year across lumps on average, in a closed universe, the size of the lump will appear bigger to us. In an open universe, the size of the same physical size lump will appear smaller because of the curvature. And if you compare these things, it turns out that in a flat universe, just like Goldilocks, the size is just right. Okay? Telling us unambiguously for the first time that we now know the universe is flat. Wonderful. Except if you've been awake, you realize there's a problem. We've proved that there isn't enough matter in the universe to make it flat, yet we now prove the universe is flat. That's a problem. How can you reconcile these two observations? Well, how could you get around all the measurement of all this matter? Well, you could have extra energy in the universe that would not have been detected in those gravitational lensing observations if you put energy not where the matter is, but energy uniformly throughout empty space. If you put energy uniformly throughout empty space, it would not be observable at all in those other things, but you could have enough energy to make the universe flat. But remember what happens if you put energy in empty space. It produces a cosmological constant. A cosmological constant gives you a repulsive force in nature. So what would you expect for the expansion of the universe? Instead of a sensible universe where the universe slows down, these are different pictures of this. I'll skip this for the moment. Instead of a sensible universe where the universe decelerates over time, we'd have a universe that accelerates over time, which is crazy. And in 1998, a bunch of observers used supernovae, those standard candles, to try and measure the deceleration of the universe, to prove that the universe was slowing down, using these supernovae and measuring them, what I talked about earlier. And they produced this curve, which may not look like much, but it shocked the world. Here's the Hubble law of expansion, and they're looking at these things. Let me draw a straight line through that curve, put everything horizontally, and the bottom line is, it turns out if the universe is decelerating, these supernovae that are measured at far, far away from us should fall on this curve. They don't. They fall above the straight line. What would that mean? That means the universe is accelerating. How much energy would you have to add to empty space to fit the curve? Exactly what you need. It turns out if you put 70% of the energy in empty space, of a closed universe, or flat universe, I should say, in empty space, 70% of the energy of a flat universe in empty space, and 30% in matter, you can fit this curve. But that's exactly what we needed. We had 30% of the energy of a universe of a flat universe in matter. We already knew that. We also knew the universe is flat. So everything fits together with this cockamamie universe that we don't understand at all. We now realize that we live in a universe, the dominant energy of which is the energy of empty space. And we have no idea why. So let's conclude with much ado about nothing. We now know the dominant energy of the universe is in empty space. We have no idea at all why it's there. No, if anyone tells you they understand it, they're lying, at least as far as we know. We don't know why it's there. We do know that probably its existence is tied to the very origin of space and time themselves, so that's why we care about it. We also care about it for another reason. It will determine our future. It turns out that the reason I went into cosmology was the wrong reason. I wanted to know whether we lived in an open, closed, or flat universe because that's the future, right? Turns out it's not. Turns out geometry is irrelevant. Once you allow empty space to have energy, an open universe can collapse, a closed universe can expand. It doesn't really matter. So the whole reason I went into it, irrelevant. Okay? In fact, the new rules are that there are no rules. Okay? We cannot determine unambiguously the future of the universe. There is one thing, however, we can determine, and that is that the universe in the long run is miserable. In fact, this was a graduation address from a private girls' school that the commencement speaker began by saying, things are going to get unimaginably worse, and they're never, ever going to get better again. That was before the last few years. What that aptly describes the universe. It turns out, if the universe is dominated by the energy of empty space, in the long run, it's the worst of all possible universes to live in. And I won't go into why, because I started late and I want to end. But it's miserable. So much for intelligent design, by the way. Now, I don't want to leave you with this misery. I don't want to leave you depressed. But let me just remind you where we're at. We have learned that of the energy in the universe, 70% is in empty space, almost 30% is in dark matter, and 1% of the total energy of the universe is everything we see. We are just a little bit of cosmic pollution. You got rid of us, the stars, the galaxies, everything we see would be largely the same. So we are truly irrelevant. Moreover, we have learned that if this is really trite, the long-term future of the universe is abysmal. So those are the two things I want you to take away. Now, as I said, I don't want you to be depressed, however, because it is truly amazing. What's more amazing than any of those things, to me at least, is here, stuck on this Earth, in this edge of this galaxy, in the middle of nowhere, we have been able to discern all of this. We've been able to understand the history of the universe back to the earliest moments of its expansion and learn about this mysterious dark energy. And understand that there's a great puzzle that remains to be solved, which is why it's worth continuing to study the universe. It always continues to surprise us. And we should therefore, rather than being depressed, we should make the most of our brief moment in the sun. Thank you very much. Yeah, let me just say,